I'm Anil Kumar, and now we will investigate higher order derivatives. The question here is, consider polynomials as displacement functions to understand the velocity and acceleration at different times. You know, velocity is derivative of displacement, is rate of change of displacement. So it is the first derivative of displacement. Acceleration is rate of change of velocity. So acceleration is rate of change of velocity, means derivative of velocity. We can also say acceleration is second derivative of displacement, and that gives you introduction to higher order derivatives. So displacement, velocity, and acceleration are very good examples in real life situation to study. So we have three different equations, and the idea of these equations is to have a linear equation, a quadratic equation, and a cubic equation, right? So to give you an idea of what kind of velocity and acceleration these displacement functions are going to represent. So if the displacement is linear, s of t equals to minus 2t plus 6, velocity will be equals to derivative of displacement. So derivative of this is minus 2. So it is constant. Do you see that? And for the second function, velocity, so we'll consider derivative of this function will be minus 10t plus 20. So that is linear. And for the third function, the velocity will be 6t squared minus 42t plus 60, right? So what we will also consider here for all our examples, all the three examples, that we'll consider that displacement s of t is in meters, right? And time t is in seconds, and t is greater than equal to 0, right? So we'll consider this for all the three examples. So what we just investigate is first part, which is about velocity, right? So we see that the velocity, so v represents velocity. So v, for all the three, if displacement is linear, velocity is constant. If displacement is degree 2, velocity of degree 1. If displacement is cubic, velocity is parabola, quadratic in nature, right? Now let us write down how will the acceleration be. So acceleration is equals to derivative of velocity, right, which you could say second derivative of displacement, and that is what we mean by higher order, right? So we'll do second derivative of displacement from now onwards for all the three functions. So it is a constant, is going to be 0. Here the second derivative is going to be minus 10t, which is minus 10, which is a constant, and here the second derivative is going to be 12t minus 42. Linear. Do you see that? So the first derivative is 1 degree lower, second derivative is 1 more degree lower, correct? So that is how they really change. Now, I hope you've understood this. As an added exercise, what you should do is sketch all the three on a graph, right? So what you do now is make graph for all this, represent this data on the graph. So that is an exercise for you. And what do you notice from the graph? Figure it out, right? So for example, this one is a linear function, minus 2t. So if we sketch the graph of this function, it should look like a straight line, right? And that too dropping downwards, correct? So straight line dropping downwards, slope is minus 2, right? Y-intercept of 6. So this one is easy, I'll do it for you, right? So others are very difficult, so I'll leave them for you. So this is my function, so I'm saying that is s of t, right? Now second function for us is the velocity. So velocity is minus 2. That means in this case, let me sketch this as minus 2, right? So that becomes minus 2, and this is velocity for me, correct? And the third function is acceleration, which remains 0 here. That means constant velocity, 0 acceleration, and that gives me acceleration at an instance of time. So of course, on the x-axis, what do I have? I have time in seconds on x-axis, and displacement, these units are meters for displacement, right? So that is how the graphs will look like, correct? Now the second function you should sketch, you could actually factor this to sketch, right? So these ones could be easily factored. That's the whole idea of taking them. So this one, just factor it. So you could write this as, you could take minus 5t as a factor. So you get t minus 4t. And so, it's a parabola opening downwards, right? So it could be something like this. So parabola opening downwards, if t is 0, then the value is minus 20, right? So if t is 0, it is, 0. So the first point is this, and the second point is 0 at 4, right? So in between 0 and 4, we'll have maximum, which in this case will be at 2. So if I write 2 here, then I get 2 times 5 as 10, and 10 times 2 is 20. So approximately 20. So anyway, what I will do is I'll just sketch a parabola here. Right, so this is my parabola. This point is 20 for us, and this point is, as you can see, 2. So these are the points on the parabola. So we'll just write them here: 0, 2, and 4. So that represents displacement for us. Now what is the line? So straight line represents velocity in this case, and the velocity is slope of minus 10. That means it's coming downwards. And what you will notice is that this turning point represents the 0 for the velocity. So if I write 2 here, you do get 0. So this turning point is the 0 of the velocity, correct? And if you draw the graph, if I write this is 0, I get plus 20. So my line is kind of like this. Do you see that? So this is the function which represents velocity for me. As far as the acceleration goes, it is minus 10. So for acceleration, I will use a different thing. So let me use this thing for acceleration this time, which is minus 10. Let us say this is, let us say this is minus 10. Okay. So that becomes acceleration for the given function. Now, that is for you as a test problem. So I'll not go there, but I'll discuss the second graph in further details. What you notice is that a turning point derivative is 0, right? So therefore, we have a 0 here. If the graph is rising, then the rate of change is positive, so this half is positive. After the 0, the velocity is negative, right? So that is one thing you notice. Second thing what you notice here is that the object is, actually speaking, if you see, is moving away, right? When you say that is your function, object is moving away. Now, if the velocity is positive, object is moving away. If the velocity is negative, object is moving towards, right? So from the velocity graph, what you also notice is velocity is positive from here to here, correct? So in this area, object moves away, right? And in this area, object comes closer. Do you understand? And this is the point which is the turning point, right? So if velocity is 0, this represents turning point for the object in motion. So whenever we are talking about object in motion, displacement for an object, in especially along a straight line, then when the velocity becomes 0, it is the turning point. If velocity is positive, object is moving away, and if velocity is negative, object is moving closer. So that is how it could be interpreted. So let me summarize this as, in a displacement time graph, velocity is represented by the first derivative, acceleration is represented by the second derivative. Velocity is 1 degree lower than the displacement, acceleration will be further 1 degree lower than the velocity if displacement is a polynomial function, okay, continuous polynomial function. That's kind of important. A turning point on displacement is a point where velocity is 0. Whenever velocity is positive, object is moving away. Whenever velocity is negative, object is closing, right? So based on these things, You need to sketch the graph. So now your exercise is sketch graph of S of t, V of t, and A of t. This is one. Second, find when is object moving away, right? And then identify turning points. What do they represent? So let that be an exercise for you. We'll answer this question later in another video. Thank you and all the best.